Hello everybody and welcome to this Max Computing webinar. I'm Alice from Macmillan Education. We're really excited today to have Shahneila and Estelle Ashman join us today. They're from Digital Schoolhouse. So please use the chat box and engage in the session. Let us know where you're from, say hello. I know there's some fun activities they've got planned for us, so please do engage as much as possible. At the end of the session, you'll receive a certificate of attendance. So make sure you check your inboxes for those ones. And then we'll also send you the slides and recordings that you can share with your colleagues as well after the session. So have a great session, everyone, and enjoy. I'll pass over now.
Thank you very much. Hi, everyone. My name's Shahneila, and I'm here with Estelle. We're both from Digital Schoolhouse. Digital Schoolhouse is very fortunate to be partnering with Macmillan Education on the Max Computing series. We run an education initiative in the UK, and we've written the content for the book. So we're going to talk a lot more detail about all of this a little bit later. So I won't preempt that by saying it all now. I'll pass over to Estelle to do her introduction, and then I'll do mine.
Hello, good afternoon from the UK and good morning to you if it's a different time zone where you are. I am, as Shahneila said, I'm Estelle Ashman. I am a teacher. I teach 2 days a week. I still teach computing. And before that, I was also head of computing in an all-through school in the UK. So teaching from grade 1 all the way through to sixth form college just before they head off to go to university. I joined Digital Schoolhouse as the curriculum content developer in 2018, which is when I then became a part-time teacher, but working for Digital Schoolhouse the rest of the time. I'm the author of Digital Schoolhouse's extensive catalogue of innovative teaching resources, and I'm the lead author on the Max Computing series.
Thanks, Estelle. And as I said, I'm Shahneila Saeed. So I also used to teach. I was head of computer science at a secondary school and sixth form, so teaching 11 to 18-year-olds for over 15 years. 10 years ago, I left teaching to join UKI. UKI is the trade body for the video games industry in the United Kingdom. We look after all the games companies that you've heard of, plus a lot more that you haven't. As UKI, I created the Digital Schoolhouse program, and am also, therefore, program director for that. So it's been 10 years sort of developing and growing this work. And as part of that, one of the key things that I've done is develop this sort of play-based learning pedagogical approach to teaching computing. And that's what underpins the heart of Digital Schoolhouse, is this essence to kind of play-based learning. And that is the approach that we've brought to the Max Computing series. And we'll go into a bit more detail about what I mean by play in a moment. And yeah, I've written a few things too. So in terms of what we'll cover, I'll explain Digital Schoolhouse in a little bit more detail so you have an understanding of how the program works here. We'll dive into a little bit about what I mean by playful teaching. And then we'll go into the book and look at student navigation and the student journey through the books and the different features, as well as how assessment is tackled within the series and looking at curriculum. Amongst that, we have time for questions. So if you do have comments, thoughts, questions, please put them in the chat. Stella and I can sort of both see that, and we'll try and address them as we go along as well. So please don't hesitate to sort of interact with us throughout. And if I talk too fast, just put that in the chat and I'll slow down, because I have a tendency to do that. Okay, Digital Schoolhouse and what that is. So it is a nationwide program across the UK. We also have a cluster in Nigeria, and so we are currently expanding internationally. But the program is really sort of set up to inspire and engage both students and teachers with computing education and the computing curriculum. As I said earlier, it was created 10 years ago. That date is significant because in 2014, the UK government brought on and announced computing was now on the school curriculum for every single school child. But we were, as a country, in a position where 2/3 of the teachers did not have the skill set or indeed the motivation or confidence to actually teach computing. There were many teachers that I saw that just forget about delivering it. There were some strands on the curriculum that were written, they just didn't understand what that was. So we was a massive undertaking for the country, where we literally had to upskill a nation of teachers. And in that environment, Digital Schoolhouse was created and born to try and support teachers. It is backed by the games industry. As I said, it's a UK delivered initiative, and so we have the backing of the video games industry. We are funded in large by the games industry and the companies there. So partners including PlayStation, Nintendo, Ubisoft, Sega, all names that you've heard of, I'm sure. And we have received backing from the UK government as well, both local and national. Digital Schoolhouse is a not-for-profit making enterprise, just to say. It is there is no turnover in profit. We rely on kind of donations. So this is not we're not a commercial program. How does all of this work? Well, we recruit a network of schools. These schools are referred to as our schoolhouses, and every school that works with us then puts forward a lead teacher, so a nominated teacher within that school that will deliver the Digital Schoolhouse program. What that teacher receives is training from us. So we connect them to the industry, the creative digital industries. They learn about the application of computing and digital skills in the creative industry. So they will learn hands-on. So this is improving their subject knowledge. We also connect with academics. And so we build in what we learn from current academic research about what good computer science education looks like. So we focus very much on how you teach computer science. And so with that training and with the resources that we develop and shape, what these teachers do is they then deliver workshops to other schools in the local community for free. What this means for a student is that if you are a student in, let's say, grades 4 to 6, your teacher might take you along to one of our schoolhouses where you spend the day there learning computing in a workshop in a way that hopefully is a bit wacky, outrageous, lots of fun, very informative and educational. And while the students are learning, the teachers are too. So the unique spin on these workshops is that it's professional development combined with student teaching all at the same time. So it's a program of support using the sort of hierarchical hub cluster model, which trains up schools and teachers and students across the country. Underpinning that are a lot of different resources, and our resources have always been cross-curricular. We're looking and tapping into sort of real-world issues and helping students really draw the connection between the computing they learn in the classroom and the computing that they experience outside. All too often, historically, when you speak to students, or certainly when you used to speak to students, they did not see all too often, this connection between computing lessons and their experience of technology, and didn't understand how the two can connect. So we bridge that world, and we bridge those gaps and help them see that and combine that through a plethora of resources. And these will range from mathematical art to cryptography, but we also have ones on games design and presentation and pitching and 3D printing and construction, and ones that look at science and recyclable materials and AI. And where we have tapped into industry expertise, it means we have gone into and spoken to the people from that industry to find out how they do things. So when we're talking about data collection and machine learning, we've spoken to data scientists who have that knowledge and asked them how they do it. We went to the games industry and said, how do you come up with a game idea? How do you turn that into a prototype? What happens when you publish a game? How do you take it to market? And we take their expertise and translate it into materials that are accessible for young children. It's a far-reaching program. We've supported literally thousands and thousands of students and teachers, and continue to increase. Those numbers are constantly out of date every time I present them. But that's a bit of a summary about Digital Schoolhouse. There's a lot more that we do. And of course, I'm going to give you the shameless plug of do visit the website to find out about all the other activities that we do if you're interested. But I want to talk a little bit more about play. I keep talking about play and being playful and, you know, no idea is too crazy, and innovation and creativity. And what do I mean by that? Play sits at the heart of what we talk about. Some people might be mistaken by thinking, well, we're video games, so actually it's all video games. It's not. Video games is the 21st century embodiment of play. It's in today's digital world. It's how we encapsulate play through video games is one fabric of it. But playing is something that is instinctively natural to us as human beings. We do it from birth upwards, and we always have done. And human beings for thousands upon thousands of years have always played games, just for a number of reasons, for social interaction, just because it's fun. This instinct, this idea that we do something just because it's fun is really, really important. And as teachers and educators, if we can capitalize on that and inject some learning into that vehicle, then we're in a win-win situation. I mean, if you look at babies, curiosity will drive them to learn about the world around them. We're very curious things as human beings. A baby will look at objects, flashing lights, make things that make sounds, you know, pick them up, touch them, interact with them, and over time learn what that response means. It's how a 2-year-old who cannot read or write is able to grab their parents' phone and find their way to YouTube and play their favorite video, which for my children, incidentally, was unwrapping 100 Kinder eggs. But it was, I'm sure we've all if there's any parents in this group, I'm sure you've all got sort of similar stories, no doubt. But you know, that the child learned, but that's not the first thing my children did with the mobile phone. The first thing they did was put it in their mouth. And when what they discovered was they couldn't eat the phone, but actually they got some sound and interaction out of it in the other way, and they learned through observation. The point I'm trying to make here is, as human beings, we never stop learning that way. We always learn that way. We see something, we get curious, we pick it up, we do something with it. What we do, though, is we stop teaching that way. We stop utilizing that as teaching. We separate the essence of play from study and serious learning. And play is relegated to just take place in the playground with the serious business of learning, where you need quite often rigid silence in the classroom, facing the teacher, taking in instructions and making notes. The other thing that I wanted, the other factor I wanted to just sort of describe to you is creativity. And creativity is really interesting, because I think when you talk about creativity in schools, quite often you're referring to, or at least here in the UK, when teachers talk about creative subjects, they are referring to art, music, dance, drama, those types of subjects, because obviously they are creative. But if you look at this definition of creativity, it's the idea that you come up with new ideas, and you realize actually that could apply to any subject. It's creative thinking. And so if you look at science, where literally curiosity is driving you to ask questions, investigate, try new things, and that's where you make your discoveries and further our understanding of the world, it's highly creative and incredibly playful. Computing and programming, again, is very, very similar. There is creative aspects to all of these things. But when we, in our language of how we talk about education, we divorce subjects like science and technology and mathematics from the application of creativity and creative thinking, when actually that is not the case. And the second one, therefore, is sort of play-based learning, and this idea that actually taking into account what we've just described, can we use the power of playful techniques to teach children? So, for example, literally using playground games, using games like hopscotch to teach students about programming, algorithms and games design, or using card games and magic tricks and storytelling. Those are all ways that we use in Digital Schoolhouse to teach computing. And so when you bring all of that together, that is literally our approach, and you bring into the mix computational thinking and all of those aspects, and that is the approach that underpins Digital Schoolhouse. And you might all be saying, actually, Shahneila, that's all fine and well, but you know, you're you're a program that delivers these sort of one-off workshops. I've got a class of students. I've got 20 lessons to teach them, 25 topics. I need to keep going. I can't afford to take the time out to just let kids tinker and explore and come up with their own ideas, because if I do, this is going to happen. They will make progress, but they're not necessarily going to get to where I need them to be. They're certainly not going to be able to learn everything that I need them for them to pass that exam. But my argument is that's why teaching is so important. We, as the facilitators, can provide that guidance and framework to actually scaffold the children and their learning, so we can help them make that progress, and using the right instructions and the right framing for the tasks and enabling them to make progress, we can allow students to go on this path of kind of self-discovery themselves that furthers the knowledge and the learning. So, for example, if I'm setting a programming task, I can devise it in such a way where I'm giving instructions for students who will naturally encounter, and maybe there'll be students among them that say, to come back to you and say, well, actually, miss, there must be a more effective way of doing this if we did boom, 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 boom. And they might be talking about iteration. They might describe subroutines. They could describe something else. And that way, that transforms really what's happening in the classroom, because the students are discovering for themselves the concept of iteration. They're just coming to you. And you, as the educator, is then providing them with the language and the means and the mechanics to implement that more easily. So it's a great way to sort of be able to build that in. But that's a lot of terminology. It's a lot of academic lingo. And you might be thinking that sounds good. What does it look like in practice? So to do that, I'm now going to pass over to Estelle.
Okay, before we have a little look at what one of our activities actually look like, I'm just going to talk about what we mean by computing. So it might not be a term you've come across before. So we use computing to be a catch-all term, an umbrella term for digital skills. So using software, being a good digital citizen, also computer science, so learning how a computer works, learning how to program, and also IT or ICT skills. So we take all of those different areas and put them under the term computing. So when we're talking about computing, that's what we're talking about. It's not just computer science, but it covers all of the different aspects of learning to work with a computer and learning to program. So let's have a little look at one of our activities. So first of all, if you haven't come across the term algorithm before, I'm going to tell you what that means. So an algorithm is a step-by-step instructions that describe how to do a task. And algorithms are often used to plan how a computer could carry out a task. Now, Shahneila is going to act as our wonderful student here, and she's going to follow some instructions that I'm going to give her to demonstrate how a computer might follow some instructions. So if you've got a pen and paper at wherever you are wherever you are listening to this session, you can join in with us. Normally, if we'd be doing this session in person, then I'd be getting you to have a go at doing this activity too. So if you do have pen and paper, you can also follow along. So Shahneila's there with her pen and paper, as you can see. So Shahneila, if you could draw a circle for me, please.
Okay.
And I'd like you then to add 2 circles near the top of the circle that you've just drawn. And then I'd like you to draw a semicircle, so half a circle, at the bottom of the first circle. And that's the end of my instructions. So I'd like to have a look at what you drew, please. Excellent, thank you very much. So this is what I actually intended for Shahneila to draw. It's the third one along, which was the smiley face. She was trying to purposely be a difficult student who perhaps followed my instructions a little bit more literally than I'd expected her to. But that's a really good example of how a computer follows instructions. You might have been, yeah, it was a face. Well done, Kenny. I purposely gave the instructions without a huge amount of detail. The reason being, we want the students in this activity to really grasp the fact that a computer needs to have really precise instructions. If it doesn't have precise instructions, it either cannot carry them out, or if it does, you'll end up with an unexpected outcome. So in this case, the computer drew, Shahneila, would you hold up your picture again? The computer did attempt to follow the instructions, but ended up with something that looked not quite what I expected at all. If I'd given her some dimensions for the circles, that would have helped. If I'd told her where to position her pen on the paper, and what dimensions the other circles needed to be, that would also have helped. And the last semicircle, I didn't tell her to join the lines up. I didn't tell her where to position the pen. I didn't tell her what size it needed to be or what orientation it needed to be drawn on either. So there's lots of ways I could have made my instructions much more precise and would have ended up with an outcome exactly as I expected. So this activity, if in the book, we then run the activity again with the students then having to think about ways that they can improve their instructions to make them more precise. And even more tricky, we also tell them that their partner, because they work in pairs on this activity, can't ask any questions. So they're learning about an algorithm by following the activity from the Max Computing series, and they're learning that a computer has to have really precise instructions, and they're also learning what an algorithm is. So the last part of the activity is then to get the student to repack and tell us what they've learned. So Shahneila, would you like to tell me what an algorithm is, and can you make reference to the activity that you've just done?
So an algorithm is a sequence of instructions to solve a problem or to carry out a given task. So with the activity we just had, you asked me to draw a bunch of circles, and I did that, and you were trying to get me to draw a face, which I didn't do.
Thank you very much. Okay, so we look a little bit more detail about the activity and the kind of pedagogy that we've got going on underneath it. So first of all, this was an example of an unplugged activity. So throughout the Max Computing series, we have unplugged activities. We use unplugged activities in two ways. First of all, activities that don't require the use of any technology. So activities that don't require you to use a computer, they tend to be paper-based. They might use drama or other practical hands-on ways of teaching computer science concepts and principles. So for example, there's a bit of dancing in there. You'll be glad to know I'm not going to make you dance. If we were doing an in-person session, I might have got you to do a little bit of dancing, and there's some music in there as well, but lots of different ways of learning about some quite complex concepts, but in a way that's practical and encourages the children to learn about something in a slightly different way by being hands-on and actually exploring it themselves. The activities often require people to take on the role of the computer as well, and it's a kinesthetic experiential way of learning. We also use unplugged activities where perhaps the teacher will model what they're going to do on the teacher computer with the students, then able to come and do the step-by-step instructions on the teacher computer. So the way that the series is written means that all of the lessons can still be taught, even if the students don't have access to their own computers. We've also made sure that the activities can be run without the need for using the internet, apart from in a couple of rare occasions where if you're teaching, for example, how to use a search engine, there are some unplugged activities, but there also is some situations where they have to use the internet to be able to demonstrate that understanding. But all of the learning can be carried out without the internet and without the use of individual student computers. So why do we use unplugged activities? They allow students to create a visual representation of an abstract concept, making it easier for students to grasp quite difficult ideas. And it's therefore ideal to use when introducing a new concept or refreshing knowledge. So for example, I use this for teaching my own students. As I said earlier, I still teach. And it also gives me an opportunity to teach concepts that would traditionally not be taught until the students are quite a lot older. So, for example, I've got some grade 4 students who are starting to learn how to do a little bit of binary code because they are able to grasp it by doing something very physical, by learning about how binary numbers work. It means that they can access the learning at a younger age than perhaps you would traditionally do that. It also aids the development of computational thinking skills. It removes the barrier of technology to access the learning. It opens the door for creative, unexpected and powerful learning experiences that engages students and helps them to dispel stereotypes. So that's why we use unplugged activities, and you'll see them throughout the Max Computing series. The second pedagogical process that we use is something called semantic waves. So the semantic wave is a way of structuring learning to really ensure that students get a really deep level of understanding. And we used a semantic wave in how I demonstrated the little algorithms activity to you. So I'll just explain how this works. So first of all, just talk to you a bit about the semantic wave itself. So it starts by taking hard to understand abstract concepts that you explain to the students. You use your technical language, but then you move on to unpacking that in ways that the students will be able to understand by using concrete things. So examples that the students would understand themselves, and using simple language that is easy to understand. You then bring in the unplugged activities like we just did with Shahneila. So we demonstrated that you can do simple step-by-step instructions to demonstrate that a computer follows an algorithm. And then, as you saw, we then repacked that learning by Shahneila talking about what did we mean by an algorithm. She reused the technical language, and she also was able to link it back to the unplugged activity that she did herself as well. So this is used again, as I said earlier, throughout the work, throughout the content of the Max Computing series. So let's have a little bit of a look at how this worked with the algorithms activity. So first of all, there we go. We looked at the definition. I explained what the definition of algorithms was and what they are. We then moved on to having a go at an activity. We experimented with representing an algorithm to instruct someone to draw a picture. And then we got the student to explain using technical language what an algorithm was. So that's semantic waves. And you'll see that throughout what we do in the Max Computing series as a way of really making sure that we're using the technical language correctly. The students are understanding using simple concrete activities and examples, but the students are always repacking that understanding at the end of the lesson so that you're really cementing that learning. The next pedagogical approach that we use is called PRIM, and we use PRIM for teaching programming. So I'm just going to go through each of the letters, and then we'll have a go at doing a little PRIM activity as well. So the first letter in PRIM is obviously the P. That stands for predict. That is the students discuss a program and predict what it might do, drawing or writing out what they think will be the output. We then move on to the R, which is run. Students run the program so that they can test their prediction and discuss in class. The I is investigate. The teacher provides a range of activities to explore the structure of the code. This involves activities such as tracing, which means looking at the variables, the data used within a program, and predicting and thinking about how that changes as the program is run. Explaining, annotating, and debugging. And debugging means finding and correcting errors in a program. And that's all done with scaffolding provided by an existing solution. So all of this so far, at no point are students expected to write their own code, and they're using an existing solution that they're given to work with. The first of the M's stands for modify, and this is where the students start to actually do some programming. They start to edit the program to change its functionality, and they do that via a sequence of increasingly more challenging exercises. Again, this is scaffolded by the teacher, scaffolded by the Max Computing series, and the students are encouraged to work through some different activities to get them to modify their code and see what changes it makes. So they're learning really and unpicking what the program does by making these changes themselves. And then the last part of PRIM, the last letter M, stands for make. And this is where students get to make their own code. So they design a new program, but really importantly, it uses the same structures that they'd already done and already learned about in the previous parts of the PRIM structure, but it involves them solving a new problem. So one of the really great things about programming is that often you can reuse the code to solve different problems, because the underlying problem itself, when you break it down and you abstract it and you take out all the unnecessary detail, you can see the actual solution is actually the same algorithm. So that's where we can start to use the same kind of algorithms and get them to encourage students to write their own programs. So what does this look like in reality. So let's have a little look at an activity. Here is a little bit of Scratch code for you. So Scratch is a block-based programming language. It was developed by MIT. It's a free piece of software, and it is browser-based, so you can use it using a web browser, or you can download it as well, so it's available offline. In fact, just to point out, all the software used in the Max Computing series is free or uses the free version, or is available free to education. So there is no outlay for teachers to need to buy any expensive software, because there is just no software that incurs a cost at all in the Max Computing series. So let's have a go at doing predict with this first example. So here is a program. In this example, the program will run when the green flag is clicked. So in Scratch, the way you start your program from running is you press a little green flag on the screen, and then it will work through these instructions. Now, what I would like you to do is, if you're feeling brave, and hopefully there are some brave people out there, if you'd like to put in the chat what you think that this program might do. So when you press the green flag, have a little prediction. What do you think this program would do when it is run? Have a look at it, think logically, think about what you might understand the blocks to do, and have a little guess. I'll give you a second, just have a little look and write something in. And I might call on Shahneila to have a guess as well, if no one is feeling brave. Oh, someone's typing, that's great. I like some brave people. Oh, we're going for spelling, making a triangle, very good. So we've got some suggestions coming in. Shahneila, what do you think it might do when it's run?
So I think it will start off by the erase all clears everything on the screen. So it deletes everything. Pen down probably means that you're going to start using the pen. It's like putting your pen down on a piece of paper, so it's touching it. And then it's got a set of instructions that will repeat 3 times. And that's sort of moving ahead. So it's like drawing a line, and then you're turning 120 degrees. And if you kind of do that again, I feel like they'll join up to make a triangle.
You are correct. So the next stage would be run. I'm not actually going to open Scratch to run the program for you, but you can imagine it literally draws a line, it does the little turn, it draws the next line, does a little turn, and it draws the last line to join up the triangle. It's an equilateral triangle it draws. And you're quite right there, Gay. It is a triangle it draws. So we're getting students to really think about what's going on in the program. By this stage, they will have done quite a lot of Scratch. So it wouldn't be new to them. They understand what the blocks do. They will have used a repeat before, and the when green flag clicks, it won't be new to them in terms of looking at the code itself. This is from a grade 4 activity, and the students then can move on to starting to have a go at investigating the program. So then they start to think about some different questions. And they tinker with the program. It's a really good word that we use throughout the Max Computing series, tinker, where they investigate and just see what's going on. So first bit of tinkering they're going to do is to change the number of steps. So they're going to tinker and see what happens if you change this number where it says move 100 steps. What happens to the program? What happens if you change the number of degrees? So again, tinkering with the program, what happens if you change that number in the turn block, the one that says turn 120 degrees? Because we really want the students to understand and feel confident that they aren't going to break anything. They're not going to break the program by changing things. That tinkering and experimenting and seeing what the output is all part of computing, even if it doesn't quite do as you expected it to do. That's all part of learning to program. And then the last little bit of investigation might be to remove the erase all block. And you end up with a bit of a mess because it keeps drawing the triangle and the different shapes that they might create all over the page, and it becomes a bit of a mess. So that's in the investigate stage. They then can move on to doing modify. So then giving them a little bit of a scaffold to work within. So in this case, they are looking at how they can adapt the program so it draws, well, you've already seen a triangle, but it might be to draw a square. It might be to draw a circle, and getting to think about how they would make changes to allow that to happen. So because they've already done the investigate stage where they've experimented and seen what different things happened, they might have worked out that they can change the degrees and make it a different number of degrees. And if they've covered this in maths, they might have already talked about that the angle in each corner of a square is 90 degrees. So they're getting to use a little bit of cross-curricular learning from their maths. And once they've tackled that and they've played around with modifying and adapting the code to make different things happen, they can then move on to the make stage. And this is where you can let them be a little bit more creative with this. So in this example, because it is actually snowing in the UK today, we went for this lovely little activity of creating a program that draws a snowman. So where they've previously in the previous task had a go at learning how to draw a circle, and they've experimented to get it to draw a circle, they can move on to getting to draw circles in certain places and having a go at drawing a snowman. One thing I just want to point out before we move on to the next, looking at the next part of our discussions of the Max Computing series, is that students aren't necessarily expected to complete all of the activities each lesson. So the way that the content is structured is the first activity, so in the prim sense, the predict section, that will be predict and run will be done by all of the students. Then the investigate and modify will be done by most of the students, and then the make, the highest level of the prim structure, will be done by some of the students. So that way the structure allows for progression within the lesson, and it allows for the weaker students to be able to still feel they're fully participating in the lesson. They're able to work their way through it, and also gives opportunities for lots of stretch and lots of extended learning for the more able students as well. So I'll show you how this works a little bit more detail as we go through. So let me show you what the student journey looks like and explain this a little bit more to you. So first of all, across all of the books, so here's our lovely grade 1 to grade 9 books. The grades 1, 2 and 3 are student workbooks, and they are write-in workbooks, so the students write in them themselves. There's lots of things like matching, fill in the gaps, short answer questions, that kind of thing, working from grade 1 up to grade 3. And then grades 4 to grade 9 are student books. They're textbooks where the student writes in their own separate notebook. So that's the structure of the full series and what it looks like. So let's have a little look at the journey through a Max Computing unit. So first of all, our units are designed to be project-based. So the students will be learning to create some sort of project by the end of the unit, some sort of product. And throughout that, they learn to design first. They learn how to create a prototype. That might be drawing sketches on paper. That might be writing an algorithm. Once they move into grade 4 to grade 6, learning how to create a flowchart to plan their algorithm. In the lower years, it might be drawing some pictures to show what they want to happen. And then as they move up into grades 7 to 9, starting to actually write text to write in English what they want to happen. They then move on to the create stage and actually start to do their programming, to creating their models. There's some 3D modeling built into the Max Computing series. So they would then create their models using 3D modeling software. As I said earlier, all the software is free of charge. And then they move on to testing and show that they've really thoroughly tested and evaluated their solution of what they've created. And they work through this as a cyclical sequence that they continue to work through. So this is really encouraging children right from the very beginning to understand that when they move, if they want to go on and go into computing in the future as part of what they do as their career, that this is the kind of cyclical nature that you tend to work in when you're creating products. You design, then you create, then you test, then you look back at things and you think, how can I redesign this to make this better? And you keep working through that process, that iterative design process. So that's built into all of our units. Let's have a little look at what a typical lesson looks like. So all of our lessons, this is a lesson from the middle of a unit. All of our lessons start with lesson objectives. These are the high level lesson objectives that describe what the lesson is going to be covering. The more detailed specific outcomes in terms of what the students themselves are going to produce, you'll find that information in the teacher guide, which goes alongside all of the student books. So you can see in this example, the lesson objectives are that the students are going to learn to use a web browser to go to websites, and also tell the difference between the internet and an internet service. Then there's an information box, which gives them the new keywords that they're going to be learning about in the lesson. You can see them in bold. Any words in bold are included in the glossary. I'll talk about that a little bit more later. And then you can see there is a lovely piece of artwork showing them what a website looks like and using call outs to identify different parts of a website. So in this case, they're learning that the header is the actual title of the website. There's a menu that allows them to navigate to different pages. And then there's the content on the page. you'll see there's a fun fact below that. We have fun facts kind of sprinkled throughout the Max Computing series, and they're just things that I've stumbled across as I've gone through writing the content, really. So in this case, it was, the fun fact here is that people typically only look at a website for a few seconds because they can't focus for very long, and that this is called attention span. And that's a really important part of web design, because you want a website to be really eye-catching, so it grabs the interest of the person viewing the website really quickly, because otherwise they might have lost interest and gone to a different website before they've even really looked at anything. There's lots of different fun facts about all sorts of different things that I found, where Shahneila was talking earlier about how we've been enjoying play for thousands of years. There's lots of really interesting bits and pieces I found out about very early games and things, and you'll see them sprinkled throughout the series. Then we've got the first of our activities. So each lesson has 6 activities. The very first activity, which you can just about see, is kind of like an orangey yellow colour. That is our get started activity. That's designed for introducing the new content. Sometimes it might be getting students to reflect on something they've learned on in the previous lesson, but it's designed for all students to get them really ready to learn in the lesson. So in this case, they're explaining what software they need to use. So writing the name of the type of software they need to use to visit websites. So this is getting them to demonstrate their understanding from a previous lesson. Then they move on to the beginner task. So the green task that you can just about again see that's green. This is the beginner level task. This is the task that's designed for all students to be able to access. And in this one, they're just showing that they can label the different parts of the website by looking at the example in the information box at the beginning of the page, and then applying the understanding by labeling this other website, which is an animals website. They have to label again the content, the header, and the menu. So they're demonstrating that they understood where these different parts were on the example, and that they can apply that learning by labeling the same parts but on a different web page. Then we move on to the intermediate task. And as I said earlier, this would then be, you're not going to have every single student doing this, but most of your students would do this activity. They're now having a go at an unplugged activity where they are given a digital resource. In this case, it's one that's printed. So you'd print it for your students. They have a printed copy of a blank web browser window. So it's got the website address section at the top, it's got the box, but there's no content on it at this stage. And then they've got a second piece of paper which has an example bit of a menu with the buttons in it, an example bit of content, and also an example header. And they have to cut it out and stick it in the right places on their web browser to show that they understand where those things would be displayed on a web page. So again, they're demonstrating their understanding in a slightly higher level task. And then the next one, the red task, you can just about see that's red. That is our advanced activity that only some of the students would move on to. But this is, again, applying their understanding. So now they're given an example of a situation where someone wants a website to be created, a web page to be created, and they're given the task of drawing a sketch of a web page to meet the needs of a particular person. So in this case, they need to create the layout of a homepage for their class website. So they're demonstrating their understanding. So they will create their idea of what that might look like, but you're looking to see that they've included a menu, they've included content, and they've included a header, and they're demonstrating their understanding from as they've worked through the lesson. The next activity, which is, you can just about tell it's a little mouse shaped, that's our take it further activity. That mouse is called Squeak. He does appear in a few of our units. Take it further activities are designed to be accessible to all students, and they're there for a couple of reasons. They're there for if you've got a little bit of time left at the end of the lesson and you want to give something for your students to be able to do, so they have something to fill in any time that might be left over. They're also suitable for that beginner student who you don't feel is able to access the next level up, but you want them to give them a task to be able to do, so they're not feeling they have nothing left to do. So they use kind of both those scenarios. And then the final activity is our checkpoint question. And this is a question that tests the understanding. This is the repacking of them showing they understood a key concept from the lesson. Now, you might notice that it's a multiple choice question and that the letters are color coded. So they are, the letter A is red, the letter B is blue, the letter C is green, and the letter D is yellow. And they go alongside some checkpoint cards that we've got as a printable worksheet, and then the students can actually hold up the color. So you can do a really nice quick little bit of checking with your students to make sure that they've understood the key concept. They can hold up the color to the answer that they want to give, and you can see very quickly and very easily that your students have understood that key concept, or if you've got some misunderstanding in your class that you need to recover a little bit later. So that's how we've structured every lesson, and you'll find this structure throughout the whole Maths Computing series from grade 1 all the way up to grade 9. So moving on to some of the book features. So I've actually talked about a few of these, but I will point out a few extra ones that we haven't discussed already. So this is a introduction lesson from the very beginning of a unit. Our first lessons of each unit go into quite a lot of detail about what they're going to be learning by working their way through that unit at the very beginning. So you can see here, this is them learning about the internet. Then again, you can see another example, one of my fun facts I've sprinkled. I discovered in my research for this particular unit that the birthday of the internet is January the 1st, and it was born in 1983. So there you go. So if you didn't know that, now you do. So there's fun facts sprinkled out throughout the units. Then you can see it's got the same structure as the lesson I showed you as an example. This is from the student workbook. So it's a grade 1 to 3, one of those first 3 books. So this is writing, where the students are actually writing into the book itself. You can see where they're drawing and ticking and filling in the blanks. And then they've got the checkpoint question where they're going to circle their answer. And as I said earlier, when they move into the grade 4 and up, we move for students to using a textbook and then writing their answers in a notebook. As I said earlier, any new words are highlighted in bold, and you'll find there's a glossary at the back of the student book with pupil speak definitions for all the keywords and images to help back up any definitions as well. So you'll find that at the back of all of the books. We also include a lovely range of digital resources with the series. So this comes with all of our, each grade. This is an example of the Scratch layout from our software guide digital resource. So this is just a presentation which shows the layout of the software. So it's there for a couple of different reasons. It's there as a quick guide for a teacher to have a quick look through, so they feel confident with what the software looks like. It's also a lovely thing that you can display on the board as students are working through activities. So if someone gets stuck and they're not quite sure where they need to click, you can just say, oh, you need to click on 1, or you need to have a look at that section that is under number 6. It can be used in a number of different ways to aid the learning in the classroom. So that's the software guide, and that's included, as I said, for all grades. We also have step-by-step instructions as part of the digital resources. These explain in detail how to do all of the tasks that are described in the student workbook or student book, and they can be used in a couple of different ways. They can either be used by the teacher, where they can then work through it themselves, displaying it on their teacher computer with the students follow along on their own computers, or it can be printed and provided to students if they're able to work through it themselves. Or if you've got more able students and you wanted to give them the digital resource instructions for a later activity, you can print it off and give it to those certain students that you know are going to be moving on to those higher level tasks quite earlier in the lesson. So you give them structure and something to get on with, and then you can focus on the weaker students who will perhaps need a little bit more input from the teacher as well. So those are included for all of the activities. So wherever they've got an activity where they're needing to carry out step-by-step instructions in software, you'll find instructions like this included in the digital resource for that lesson. So assessment, how this works within the Maths Computing series. As I said, we've got progression built in and assessment built into the lesson itself. So because certain students won't necessarily complete all of the activities, you can use that as a way of assessing their progress. So you might have certain students that only achieve the beginner and intermediate tasks. Then you know that they're working at the intermediate level for that particular unit. If you've got students that then do all of the up to the advanced activities, you know they're working at an advanced level for that activity. And you can see the learning objectives are given for that particular lesson at the beginning of the lesson for that. So the beginning of the spread for that lesson. Alongside that, you've got the teacher guide. Teacher guide goes through in detail the kind of answers we're expecting from the students, so your teachers can feel really confident that they are able to mark the answers that the students are giving really confidently in their workbooks. So that's included alongside the student book. You can also see the learning objectives that the students are achieving, and you can see and here we've got an example of the lesson outcome profiles as well. So this is what we're expecting the students to produce as part of the lesson. So as I said earlier, the learning objective is included in the student book as a high level learning objective, but we've got that breakdown of what we're actually expecting the students to produce within the teacher guide. And you can see that's broken down again into beginner, intermediate and advanced. So you're really given a lot of detail on what we're expecting the students to produce. So you're able to make a really confident assessment of where the students are working at in each lesson. And then the checkpoint question, as I mentioned earlier, again is used at the end of the lesson just to check the core concept has been really well understood by the students. At the end of each lesson, end of each unit, there's a test or an assessment, and this increases in complexity and number of questions as you work through the grades. So this is from an early book, I think this is in grade 3. So it has 6 questions in it. This is a write-in example from one of our student workbooks, and as they move through the grades, they start to work on answering the questions in their notebook. So in this case, it's write-in because it's from grade 3. And you can see that they're saying what software they use to write their case files. So in this particular unit, they are investigating a missing person. So it's a really lovely activity where they're doing some code breaking and learning about how to write in a word processor while they're solving this mystery. So they have to say what software they use to write their case file. They have to use correct capital letters. So they're then saying what key they had to use to make capital letters. And then they're having a go at demonstrating some of the code breaking they did. And you might notice that question 3 is structured like a spreadsheet. So they're starting to learn some spreadsheet skills in this particular unit as well. So that's what the assessment looks like. And then the answers for that are given fully in the teacher guide as well. As part of the teacher guide, we also have a passport, which can be used to demonstrate a student's progress through each of the learning objectives. And as part of the teacher guide where the answers are given to the test, so here's the test, apologies. Here's the test, and you can see the answers are given at the bottom for that particular test. But you can also see the learning objectives are then highlighted for which question covers which of the learning objectives, so that you're able to tick them off in the passport and be able to demonstrate that the students have really fully demonstrated their learning of that particular objective. So a little bit about the curriculum that we've used and we've developed throughout the Maths Computing series. First of all, we've made sure that we've used a cross-curricular approach to maths computing. So you will have noticed, as we've talked about a few different things, that we've used a little bit of maths already. We've talked about how we used a bit of art in demonstrating how an algorithm is following instructions. I also talked to you a bit about how we use some dance. We've got a unit that uses music because music, especially when you start to look at computer-based music and programming music, it's a really nice way of getting students to think about how programming works, how sequences, how repeating sequences of instructions works. So that's one of our units based around music. There's a unit based around writing an interactive story, so getting them to bring some literacy skills to their computing lesson. And we've also got a unit where they develop a game where they have to demonstrate their understanding of nutrition, and they program their little character to catch the right kind of food. So if they catch, for example, fruit and veg, they get points, and if they catch cake, then they get negative points, that kind of thing. So they're demonstrating their understanding of cross-curricular concepts while learning their computing skills. So the Maths Computing series delivers a curriculum across 6 strands. So as I said earlier, computing is a catch-all term, an umbrella term for various different areas of the curriculum, and they cover algorithms, which we've talked about, programming and robotics. Don't worry, as I said earlier, we've developed the series purposely, so there's no expensive kit or software needed. Robotics is taught in a number of ways, using some wonderful software where students are able to simulate robotics, but also things like unplugged activities. So there's one really fun activity where the teacher becomes a sandwich making robot and follows the students' instructions to make sandwiches. It sounds weird and wacky, but it's an amazing way of students learning about instructions and giving the correct instructions in the right order. Data, so learning about spreadsheets and databases, also learning a little bit about binary code as they move up towards the end. And we also have digital skills, so the students are learned about different ways of using software to develop different kinds of projects, including video editing and web design, hardware and software, so learning about the different parts inside a computer, and also the software and how that works as well. And finally, we also cover communication and digital citizenship. So we make sure the students are really well versed in understanding how to be a really good digital citizen, how to stay safe while they're online, and e-safety tips as taught throughout the curriculum as well. So just to finish off, we have our full coverage of our curriculum throughout the grades from grade 1 to grade 9. You'll notice that we have golden ideas, which are key concepts that are taught throughout the different strands and how they are covered in each of the grades. And grades 1 to 3, there's specific learning objectives for grades 1 to 3. And the golden idea is then it's then covered in the next grade up as well. So from grades 4 to grade 6, the same golden idea is covered, but then the learning objective is developed further for the older age groups. And the same thing happens once they move up into grade 7 to grade 9. So that is the end of our talk about the Max Computing series. So hopefully you found it really interesting. Here is our contact details. If you want to find out more about Digital Schoolhouse, or you have any questions or queries about the Max Computing series, do please feel free to contact us. And you've got our X handles there, or what would normally be called Twitter handles. And thank you very much.
Thank you so much, both of you. That was really, really great. I hope everyone found that interesting and are as excited about Max Computing as we are. So as I said at the beginning of the session, you'll receive certificate of attendance in your inboxes. So please do look out for those. We'll also send you the slides and session recording as well. So you can let your colleagues know that the session's been recorded and they're able to watch the on-demand session and still receive a certificate for themselves for a short period of time. So we'll also send you a link for where you can register to view digital copies of the available Max Computing workbooks and student books, and also the teacher guides. So make sure you have a look for those as well. So thank you again, both. That was really great and getting lots of great comments as well. So we'll leave the webinar now and hopefully see you on the next one. Thank you very much, everybody.
Thank
Bye.
you.
Bye.
Bye.